Hello everyone, welcome back to Electronics 1. We're going to pick up from where we left off in the last lecture, and that was analyzing a common emitter amplifier. Last lecture we analyzed the small signal gain. Now, and as we ended the lecture, we mentioned that other parameters we're interested in with amplifiers is the input and output resistance. So let's have a look at input and output resistance. I'm just going to say I have a common emitter amplifier. Okay, and let's see if we can assess the small signal equivalent circuits to evaluate those. Okay, so I'm going to use a hybrid pi model to begin with, and we'll see that I'll eventually move to a T model for the analysis when I add in the emitter resistance. Okay, so I guess just to be clear here, I'm going to start and do the analysis assuming that RE has been bypassed. Okay, so I'm just going to say without RE because it's been bypassed with a bypass capacitor. Okay, so for this analysis the hybrid pi model works well. So the other thing I'm going to do here is I'm going to if you look back at the last lecture, I showed RB1 and RB2 as two individual resistors in parallel. I'm just going to show them as a single resistor here that's that has a value equal to RB1 in parallel with RB2. Okay, and of course I have my input, my small signal input applied. Okay. Because I have no my emitter resistor is bypassed, my emitter is connected directly to ground, my collector we know is connected to ground through a resistor RC. Okay, so again I'm interested in two things: input resistance and output resistance. So I'm going to call the give the input resistance a couple of different names here, or maybe it's better to say that I'm going to look at it from a couple of different perspectives. I'm going to look at the input resistance from right at the base of the circuit, and I'm also going to evaluate the input resistance, maybe we'll call this REN, from the perspective back beyond the bias resistors, those RB1 and RB2, okay, because those are going to impact the input resistance from the perspective of the small signal source that's applied. On the output, I could look at the output resistance from right at the collector. Let's call this RO prime, but well, let's come back and talk about that in a second. Or I could look at it from the perspective of the output voltage and look at the output resistance including that bias resistor RC. Okay, let's look at the output resistance here first. Give myself a little bit more room here. We'll look at these first just because they're simpler. So when we assess, if you think of when you've done Thevenin equivalent circuits, or you'll assess the resistance looking back into a circuit, voltage sources you short out and current sources appear as open circuits. So from the perspective of the collector directly, the output resistance here, RO prime, is going to appear infinite because this appears like an ideal current source, so RO prime is infinite. Okay, whereas R out, when we take into account the bias circuit, looking back from the perspective of the where the output is taken, R out is equal to RC. Okay, and one way of I think it's pretty obvious here, but one way to assess the resistance at any point in a circuit, looking back or looking forward, is to apply a test voltage, let's call it Vx, and assess what current flows from that test circuit. So what current Ix flows. In this case, the only path Ix has to flow, right? No current's going to flow this way, because again this appears as an open circuit. So our only path is through RC. So if we calculate the resistance Rx, well in our case this is R out, is going to be equal to Vx over Ix, and that Vx is going to appear right across RC, so the output resistance is directly that, it's RC. Okay, because again RC is the only thing that is limiting the current Ix if we think about evaluating it using a test source like I've done here. Okay, I think it's almost easier in this case to just assess it through observation and note that the only resistance that's seen looking back from the perspective of the output is the collector resistance. Okay, and we can use a similar approach on the input. Again, you could connect a test source to evaluate the input resistance, but again we can just through observation here I think pretty clearly see that in this case, because the emitter has a connection directly to ground, and I could show that emitter connection to ground over on this end if it makes it more clear. So from looking in from the perspective of the base directly, the path to ground, the only resistance in the path to ground is R pi. So R in prime is equal to this R pi, this base to emitter resistance in our hybrid pi model. If I take a step back and look at the input resistance from the perspective of the input source, well, now we can see that I have R pi in parallel with RB1, RB2 from that perspective. Okay, so R in here is going to be equal to RB1 in parallel with RB2 in parallel with R pi. Okay, so simple enough, but what about the input and output resistance with RE? Okay, so no bypass resistor around RE. So your first thought might be, well, let's just go up to our hybrid pi model here and oops, and let's replace this connection to ground with this emitter resistance, and let's reevaluate our input resistance. Okay, well, this is not straightforward, because my looking in from my base here now, I have the current that's flowing into the base, or the base current here is flowing through R pi, but RE has a different current, has IE flowing through it. Okay, so it's not straightforward to assess the input resistance using the hybrid pi model because we have two different currents flowing through those resistors, and we have to account for that. So here we'll discover that it's actually easier to use the T model. So let me remodel the circuit using a T model. So rather than R pi, I'm going to have my intrinsic emitter resistance in series with my external emitter resistor. Okay, this is right away we might note that both resistors here are at least passing the same current. That's the emitter current. Okay, and of course let me just finish showing my external bias components. So I have RC, and then on connected to the base, again I'm going to show RB1 and RB2 as a single resistor that has a value equivalent to the parallel value of RB1 and RB2, and then I'm going to apply my input, small signal input, to the base. Okay, and right away you probably note that the output resistance here has remained unchanged. Doesn't matter which model. This current source appears as an open circuit again, so my output resistance from the perspective of where my output is taken is still equal to RC. That's the only resistance it's seen. Okay, so that part's straightforward. But let's look at the input here again. So my input, let's call this Rn prime, looking in directly at the base, and my input from the perspective of my source is, let's just call it Rin. Okay, so at a first glance I could say, well, Rin is simply equal to Rin prime in parallel with RB1 and RB2, and that would be true. But what is Rin prime? Okay, this you might your first thought might be, well, it's just equal to the intrinsic emitter resistance plus Re. The problem is here, from our perspective here, the current that's flowing in from the point we're looking at, the base, is base current, but it's emitter current flowing through those resistors. So we have to account for that when we assess the resistance here. Okay, let's look at how we can assess this input voltage at the base, this Rn prime. Okay, so like I showed for assessing the output voltage, although it was a very simple case and we could assess it just through observation, here you'll see the true value of applying a test voltage to assess the resistance here at the base. Okay, so just drawing a section of my T model here again. Okay, and so again, what I'm hoping to find is what the resistance is here, looking in directly into the base. And one way of doing that is to apply a test voltage. Well, let's apply a test voltage Vx, and if we can calculate how much current flows Ix as a result of that applied voltage, we can then find the associated resistance looking in from that perspective. Okay, so Vx here, you should be able to appreciate, is going to be equal to the voltage drop across these two resistors. Let me just move this label here. That voltage Vx is going to be the voltage drop across the intrinsic emitter resistor and the emitter resistor. That voltage drop is going to be a function of the current that's flowing through those resistors, which is the emitter current. Okay. Oops. So that emitter current times Re plus big Re will give us that voltage drop Vx. The current Ix, well, that current is going to be the same as our base current. Okay, so current Ix is equal to our base current. Okay, so Rin prime then, or the voltage looking in from the point where that test voltage is applied, is going to be, just based on Ohm's law, is going to be equal to Vx divided by Ix. And I just said that Vx is equal to my emitter current times my intrinsic emitter resistance plus that external resistor. Ix is equal to Ib. Okay, but I can write IE in terms of the base current, so I know that IE is equal to beta plus 1 times IB. Okay, so this is simply another is equal to IE. Okay, so that all times little re plus big Re is equal to Vx divided by IB. Okay, here we see that these IB terms can be cancelled, and I'm left with an input resistance here looking into the directly into the base that's equal to beta plus 1 times the intrinsic emitter resistor plus the resistance of that external resistor, that emitter bias emitter resistance. Okay, you might recognize that beta plus 1 times Re is actually equal to R pi. Oops. So this part of the expression is R pi. So R pi plus beta plus 1 times Re is another way we might express the input resistance. And if you think about this for a second, it makes sense that the resistance is not just the resistor of these two resistors. Circle those with a different color here, because these two resistors are carrying a current that's beta plus 1 times larger than the current from the point I'm looking in at. So those resistors are scaled by beta plus 1 times. Okay, so that's we've gone through and calculated or observed the input resistance and the output resistance of a common emitter amplifier circuit. And just I guess to be thorough here, remember that the total input resistance here Rin, we stated up here, well, this is now going to be beta plus 1 times Re plus big Re in parallel with Rb1, which is in parallel with Rb2. Okay, so that's the total input resistance as seen from the perspective of the source. Okay, so if we want to summarize our common emitter amplifier, one of our classic common emitter amplifier configuration, we might summarize in two instances: when we have an RE or when there's no RE. So RE is bypassed. So with RE, our voltage gain, we discovered, let me maybe put this in the form of a table here. My small signal voltage gain was equal to alpha RC minus alpha RC over RE, small RE plus big RE. But when RE is bypassed, it's minus alpha times RC over little RE. My input resistance, I'm just going to say the input resistance prime here, looking directly into the base. Again, the input resistance from the perspective of the source will depend on the external bias circuit, and we've accounted for those in our observations up above. But just looking directly from the perspective of the base, it's equal to beta plus 1 times RE plus little RE plus big RE. Or with no with the emitter resistor bypassed, we saw that it was simple to evaluate, that it was just equal to R pi, and we remember that R pi is equal to beta plus 1 times RE. The output resistance, looking from the perspective of where the output is taken, is in both cases, whether we have an emitter resistor or not, is equal to that external bias resistor connected to the collector, RC. Okay, so that summarizes the properties of a common emitter amplifier, and we have all of those things that we like to know about a voltage amplifier, right? What its voltage gain is, what its sorry, not a voltage amplifier, maybe just an amplifier in general, what its voltage gain is in this case, what its input resistance is, and what its output resistance is. Okay, and we see that they're dependent on those bias components. Is this these properties of a good voltage amplifier? Well, it depends on some of these values here. The gain can be reasonably high if we bypass our emitter resistor. Our input resistance for a voltage amplifier, we would like to be quite high. So it's beta plus 1 times RE. So RE is usually a fairly small value. You know, we've talked about 25 ohms being a common value, but it is beta plus 1 times larger than that. So we have a value of beta of 100, then we have a reasonable size input resistance. Our output resistance is a function of that collector resistor. So we again, depends on the value of the collector resistor. So some common circuits may have a collector resistance of 1 to 2K. So in that sense, the output resistance might be a little high. So from that perspective, maybe this isn't a great voltage amplifier because its output resistance is not what we would ideally like to see as 0. Okay, so over the next couple classes, we will do the small signal analysis for our other two configurations of small signal BJT amplifiers, and that's common base and common collector amplifiers, and we'll go through and try to summarize these properties for each of those amplifiers as well.